Ele vai falar sobre o uso de Lua com Nginx na Shopify. Uma salva de palmas para ele, por favor.
Hello? Yeah, okay. So hi everyone, I'm Xavier. I work with Shopify on the production engineering team. And I'm going to be talking about how we've built intelligent load balancers, as we like to call them, using Lua and Nginx. So I'm actually French originally, and I lived in the US. I went to school in Montreal, though, which is where I discovered Shopify. And when I returned back to the US, I've been working for them remotely. Shopify, on the other hand, is a Canadian-based e-commerce platform. It has over 275,000 stores, and we've had $7.7 billion of GMV, or essentially the money our merchants see, go through our platform last year. And we're dealing with fairly large numbers. So we have 800,000 requests per minute flowing through our system during the average day. And we actually have 1,600 employees now. So we're growing pretty rapidly, and we're still hiring. On the other hand, intelligent load balancers. So the first question I guess most of you are asking is, what are intelligent load balancers? So your typical load balancer, just like a normal Nginx or Apache, will just do these kind of very basic tasks. Like it'll terminate your SSL. So that means that your main applications don't talk about SSL. They don't worry about that. It'll do stuff like redirect rules. So you can say, take this address and actually point it to this other address before sending it to my real servers. It'll, of course, balance load between your servers so that you can keep adding more and more traffic. And it'll do stuff like proxy application servers that might be sensitive to load and various things and just help shield your application. But LBs can actually do a lot more. And so I'm going to be showing how we've done stuff like application-specific routing so that we can route, we can take into account application concerns such as database sharding and capacity of various areas of the application when we're routing traffic. We can serve our caches directly from the load balancers, so we don't actually have to travel all the way down to our application servers and do a bunch of logic before just serving a pre-made response. And for areas we can't cache, we can just do stuff like throttle the amount of traffic that goes through and control user experience at the same time. Of course, within Shopify, we do a lot more with this. We have a bunch of different middlewares and modules that we use to load balance. So a little bit about Nginx before we get into the Lua meat. Nginx is an open source web server. It's really, really fast. It's worker-based. Each worker can handle about 20,000 simultaneous connections, and it's all evented, so it's very responsive on each one of those connections at the same time. It has a very extensive C API, but no actual Lua API. Yeah, it's open source. So the real question for us is, we'd already been using Nginx. We wanted to do more with Nginx than what we'd already been doing, and so we wanted to see how we could avoid using C for application problems. And so that's why we've ended up using OpenResty, which some of you may already know, but for those who don't, OpenResty is also an open source project that hooks into the Nginx API and exposes it all to Lua. So at the end of the day, you have 4 different phases of API. You have your initialization, your rewrite phase, your access phase, and your log phase. Essentially, that means that you can run some code at startup, run some code when the request comes in, run some code when the request goes out, and run some code after the request. And so to us, this has allowed us tremendous flexibility. We can do stuff like send requests to random servers whenever we feel like it, or add various logging information on the inbound and outbound parts of the request, such as marking where what actual of our servers responded to that request so that we have information about that for debugging. OpenResty actually uses LuaJIT, so it's actually crazy fast, at least for us who come from Ruby. So we're used to very, very slow responses. When we first deployed our first modules, these were actually the logs. And so to us, this looked like a bug because the logs were just flat and at 0. Turns out we were measuring in milliseconds instead of measuring in microseconds. So we've been very happy with the performance we've gotten. And we've developed this set of modules or middlewares that we call Nginx routing modules. We have 30 different middlewares here for a total of 28,000 lines of code, which it's not huge, especially by the standards of a 1,600-person company, but each one of those lines of code actually matters tremendously towards the health and performance of Shopify. And before I dive into some of those, I'm going to give a very quick overview of the actual architecture of Shopify, because some of these will deal with this directly. So Shopify has always been a very fast-growing company, but in 2014, we finally had to make the decision to shard our main database. We grew too much, and so we had to split up the database into a bunch of identical copies that hold a fraction of the total data. This means that each shop will be on a single shard, and a shard can have 20,000 shops on it instead of holding 200,000. This has allowed us to scale much more and just keep adding more and more customers. And that was a great step forward. But the issue we had the year afterwards is that one shard crashing still took out the rest of the application. The rest of the application was still written in such a way that we assumed all of Shopify was working at any moment in time. And that's not something that holds when you start having a dozen different services that all interact with each other. So in 2015, we implemented a bunch of resiliency primitives so that we make sure that we're guarding against any potential failures. And if your database goes down, you try to stop any more requests coming in, and then you wait for it to come back up before hammering it again. And now we're trying to take this a little bit further and finish it off with a project we call Pods, where we want to fully isolate Shopify and actually make it a bunch of mini Shopifys, so that then we can just add one like in Google's cloud, or delete one whenever we feel like it. And so a pod is a fully isolated section of Shopify that can serve requests on its own, that can scale on its own, and that most importantly can fail on its own. They do still share one common global part, and that's going to be the load balancer. We still share the same load balancer because at the end of the day, it's still running in a single data center, and a data center will have multiple pods, and they all need to access the internet. And so the load balancer's job is going to be figuring out which pod a single request comes in. So it'll see a request for some specific URL, and it needs to be able to say, send it to this part of our data center that has the actual data that you need to respond to this. And this method also needs to be resilient to any failure of other pods that are unrelated to that request. So you can't just do something like send it to everyone and see who responds correctly or things like that. And so we've built a system called Sorting Hat that solves this. Sorting Hat acts kind of like the Harry Potter sorting hat. It looks at a request and extracts pod information. So a pod information can come from basically any data that's sent along with the request. And so we have this general kind of flow for our request where we start off with a domain lookup, and we just try to answer it based off the actual domain of your request. So I have a little example here where you can see this is Kanye West's store. So if you ever want to buy really expensive shoes or ripped up shirts, this is where to go. We have the advantage, though, that in this case, he has his own domain. And that domain uniquely points to his shop. So that means that whenever you request something for YeezySupply.com, we can just look at that domain and then look at our table that maps domains to shops to identify what store that you're trying to access. So Sorting Hat will actually look at this information and then just short circuit. We've already found the correct shop, and so we can just send your request off to whatever pod Yeezy Supply happens to be on. But we have a lot trickier situations where we'll still have a bunch of various services that are provided by Shopify to make the life of merchants easier that are hosted on Shopify servers, on Shopify's domains, fully Shopify owned, And so as a result, we can't just look at Yeezy supply to determine where we want to be going. Instead, we have to find some other part of the request. And so oftentimes what you'll see is that the shop ID is actually directly embedded inside your request. So in this case, this is to sign up for Amazon's marketplace, so that if you want to sell products on Shopify, you can also be selling them on Amazon at the same time. And so to build a system in a more systematic, well, to systematize this, this problem, we built a URL router. Our URL router is basically centered around this table of tables. We'll have these important portions to the table, notably a pattern, which ironically enough is not a Lua pattern anymore. It's actually just a normal regex. It'll have a list of HTTP methods. It'll have a name for debugging, and the key part is going to be the method. And we'll get to that in a second. And basically what happens each time a request comes in, we'll go through, we'll match the pattern on the request URL. We'll match the HTTP verb, because some URLs are only valid for a GET request or a POST request or some types of requests, and they might have other methods of handling different kinds of different verbs. And then we'll apply the method, passing in any capture groups from our regex match, any sort of information we've collected from the actual URL, and make a determination of where our request should be going. And so the interesting bit is actually the method. So the method is just open, it's just a normal Lua method. So at the end of the day, you can do anything you want with it. You can look at post data, you can look at user agents, you can look at query parameters, you can do any sort of things you want. And we already have over a dozen different methods implemented in our code. On the other hand, yeah, as I've mentioned, the pattern is actually not a full, it's not a pattern, it's a full regex. We had issues with that I'll get to in a second. So we have 397 rules currently. We have 397 of these entries in this table. And maintaining them and writing them manually really, really sucks. And so we've been wondering what we could do to auto-generate them. And so we've developed a system within our applications where we just have a script that will actually automate this entire process. And it looks like this. Sorry, could I get some water? It basically outputs a JSON blob that we will load into the load balancers that looks the exact same. Then what? Yeah, I just need a second. Right, so as I was saying, we'll just output this JSON blob and load them up into our load balancers and use that instead. Sorry, this is actually my first talk, so I'm getting a little bit nervous. It was a lot easier in practice. Right. So in a totally different, sorry, that was Sorting Hat. So Sorting Hat will take care of essentially routing every last request that goes through Shopify and identifying where specifically in Shopify we can actually answer that request. And so we've developed this fully automatic system to do that. But then we have other systems like edge cache. Edge cache originated, from Kylie Jenner. And the core of the thing is that people really, really love lipstick and makeup. They really love lipstick and makeup. This is just a little graph of traffic within Shopify. And you can see exactly when Kylie started selling her lipstick. And so, yeah, it's caused us a problem because they actually love it a bit too much. Oops, what just happened? Yeah, I guess it'll be a little bit cut off, but that's fine. Right, so they actually loved it a bit too much for us. And you can see this is the response time during that same sale. Basically, it was completely unexpected and overwhelmed everything that we had in place. And we're just lucky we didn't take out the rest of the platform at the same time. And yeah, this is kind of a it's kind of a great problem to have because, you know, it's too much success and it allows people like me to have fun making geeky optimizations to our platform. And what we came up with is a system that's called edge cache. For a long time, we'd been using, we use CDNs, we use all sorts of services to hold information that, is static and doesn't change very often so that we don't have to take those hits. But in some situations, those caches don't work very well because they don't know anything about our application. They don't know how Shopify works, when it changes, or things like that, and we do. We can say exactly when you need to update the cache. And we'd like to do stuff, we have, like, for example, customer accounts. So you can log into Kylie Jenner's website and you can have your own account with all your personal information there. So that when you check out and buy lipstick the next time, you don't have to enter your credit card and you don't have to do all that kind of stuff, and you can just go click, done. And we'd like to cache that. That obviously breaks most caches because they just assume everyone sees the same thing, but we'd like to say, hi Xavier, welcome to Kylie's Lip Kits. What color do you want today? And so edge cache instead is a system written in Lua that generates app-specific keys. So each application might have different requirements on how unique something is. So for example, the main Shopify application will consider cookies and their URI, the URL for caching. And so then it stores all that kind of information in cookies to make sure we don't mix up pages accidentally. But then a key point along with that is that we actually don't aim at caching things for long term. The objective here is not to serve as much traffic as possible outside of Shopify. It's to serve enough traffic rapidly that the rest of Shopify doesn't suffer. We're fine with having a lot of requests come through as long as we can actually answer those requests. And so this system actually has saved us multiple times during future Kylie sales, where you can see this is about 2 weeks after that first sale I showed earlier. And by this time, we'd finished the first version, and it basically took care of all of Kylie's traffic. We had 0 exceptions, we had 0 latency increases, we had 0 of anything, and the rest of the Shopify didn't notice that we were selling 100,000 lipsticks in 20 minutes or whatever crazy numbers she obtains. So this kind of system has served very well because Lua being fast enough, much faster than Ruby, doesn't require nearly as much time to just serve a plain HTML page to the web. But it still causes us, there's still some areas that cause a lot of problems, noticeably checkout, because you still have this massive horde of people coming in and are like, I want my lipstick. And things like checkout are a lot trickier to cache. You can't just serve the same checkout page to each person. Every single person is going to have a different one, and only 100,000 people are going to actually get their lipstick. And so it's way trickier to actually scale up, because on every single step of your checkout, you're going to be checking, is there still a lipstick? Is there still Cocoa Red, or is there still 22, or So Sexy, or whatever? And so you actually can't just serve a cache. Instead, what we determine is that you have to throttle it. We can only check out so fast, and we're trying to make that always go higher, but there's only so much that we can do. And so if we go above that, we want to just make everybody wait instead. And so we were developing the system. We added 2 extra requirements to the thing, which is one, it should be stateless, or what we call globally stateless, which is we have a bunch of load balancers, but we don't want them talking to each other. We want them to be completely ignorant of the rest of Shopify. They each see their own little window of it, and so they shouldn't be talking to each other. And then we want it to be fair, so that if you enter the checkout queue before I do, usually you'll get your lipstick before I will. We can't always guarantee that, but usually. So this is kind of what we ended up with. We basically, whenever the checkout throttle is turned on, users will hit a waiting page served statically in Nginx, and in the background, every 5 seconds, they'll just keep hitting our load balancers. And inside there, what we'll be doing is running a PID loop. And so a PID loop is just this like basic control mechanism where you measure some value, you produce an output, and you see how it affects your overall system. In this case, the value we're going to be measuring is going to be the amount of checkouts happening. We want to make those checkouts happen as close as possible to our limit. And the value we're going to be adjusting is going to be our queue lag, which is essentially, the time at which you entered. And so when you enter the actual queue, we've written down a cookie with the time that you entered. And then each time you ask to go through, we look at that time, and we look at the lag, and we say, like, oh, you entered 5 minutes ago, and the lag is only 2 minutes. That means you've been waiting for very, very long, so we'll let you in. But if you entered 5 seconds ago and the lag is 2 minutes, then we'll just say, you have to wait your turn. And so the result is that as more and more requests keep going in, the PID loop will just keep increasing that lag, so that only the oldest people get to go in. And as there's more and more free capacity, it'll decrease it, so that we can just start shrink the overall queue and just start accepting more and more people. And so this system has actually solved all of our social media issues, which were a huge problem for us, because at the end of the day, nobody cares that Shopify has difficult technical problems. They just want to buy their product, and so they blame our merchants, who then blame us and then leave. And so this system has actually been probably one of my favorite projects to implement in Lua and Nginx, just because it had a bunch of subtleties in writing that PID loop and making sure that we're actually keeping everything fair-ish. Yeah. And then there's another major area of our Lua usage, custom load balancing algorithms. Basically, by default, load balancing algorithms are not actually well suited to a lot of different applications. They have very generic algorithms, which, for example, round robin, where you just give one request in sequence to each one of your backend servers, or random distribution, which is similar, or a few different other things. But that makes a lot of very general assumptions, and there's often something more specific to your use case that would work a lot better. And choosing a bad algorithm means that you can actually increase the latency for your users, and you can even cause errors as you end up overloading specific servers. And so, it solved these kind of problems where, for example, we don't actually have the same servers everywhere in our data centers. We'll have some older servers. We can't afford to always buy brand new servers. And these older servers cannot handle the same amount of traffic as our newer ones. So we want to make sure that we're sending less traffic to older ones and more traffic to newer ones. And for a long time, we were sending the same amount of traffic to old ones. So they would just kind of die in front of us. And then you also have heterogeneous loads. So checkout, as I mentioned, is harder to process. It takes longer to actually handle a checkout request than it does to handle a storefront request. And so we'd like to make sure that if a server is handling a bunch of these difficult requests, that we don't keep overwhelming it and end up taking out the rest of that server. You also encounter issues with queuing behavior. So in 2010, this made kind of tech news because Rap Genius, now called Genius, noticed that Heroku changed the way they were routing traffic. And it basically violated a bunch of assumptions in Rails and would cause them to pay 50 times more to get the same performance. And so you have to be able to take this into account with your load balancing algorithm and see, like, okay, if we want to serve a Rails application, we should use this kind of queuing, this kind of algorithm, and if we want to serve a Node application, we want to use different kinds of queuing. And you can also have a bunch of secondary concerns, such as like request priority, where certain requests are more important for you, and so you'd rather serve those and let other ones fall over. And that's less important, but it still matters. So OpenResty exposes Balancer. It should be Balancer by Lua, which basically allows you to specify your own Lua load balancing algorithm. And in response, we had an LBAFO, or load balancing algorithm face-off. We developed a few novel load balancing algorithms. First one is the death ray. It sends every request to the same server until it stops responding, and then moves on to the next one. So it's good for progressively wiping out your application. We also built a mobile-first load balancing system. It will restrict the capacity of non-mobile users because mobile is the future, and so we should be encouraging that. It'll also give a small fraction of that mobile capacity to BlackBerry and Windows because nobody should be using that. But there are also some serious people who built real algorithms. So we have deterministic hashing. This is something that Google uses. The idea is that requests from one client should always go to the same set of servers. And so the way you determine that is through some specific algorithm that looks at the IP and the shop you're trying to access and basically says you get to access this 5% of Shopify's servers, and every single request will always hit one of those 5%. And so that's useful if, for example, you have like an attack where somebody's attacking a store, because if you're randomly routing, you'll hit every single of the Shopify servers and spread your attack across our entire system. But if you're doing deterministic hashing, you'll only kill 5% of the system, and then we'll just let you die. A version of this approach is actually the system that Google uses when you hit Google's traffic. You don't actually see all of Google. It just gives you a small portion. And then the other one we've built is EWMA, or exponentially weighted moving average. Basically, we look at the amount of time you take to respond to requests. And we track that average, weighting it so that more recent requests matter more. And then we try to basically balance it out so that if we give requests to the lowest latency hosts. And this is actually what we're using now. This allows us to have older and slower hosts and not overwhelm them because they'll take longer to respond, and so we just won't send as much traffic to them. And I have 1 minute left, which is good because this is super short. We've also built this kind of fun and super useful module called HTTPDB. It's the only true web-scale database. It's not actually a database. It's basically just a wrapper around a Lua table that lets you access it from the internet. well, from our intranet. And it's used by, we use it to do configuration. So basically, we can access configuration tables and set their values in real time without having to restart our application, which is useful because we'll configure, for example, the load balancing algorithm. We could say switch the load balancing algorithm right now, or turn on the throttle, and a bunch of different things like that. So there we go.
Hello, thank you for your talk. My name is Felix, and I also work in a e-commerce platform here in Brazil. We also use Nginx, but we're not using OpenResty. We always the group responsible by edge, cat, routing also are always a little afraid of OpenResty. It's not always with the last release of Nginx Core. And I want to know if you guys had some kind of problem, kind of emergency to get some release from Nginx Core to put on OpenResty if it caused some problems in your history. And
so the question is whether or not OpenResty isn't always the latest version of Nginx. And so he was asking if we've had, Felix was asking if we've had any issues where we needed to do an emergency upgrade. Yeah, go ahead. And so we haven't had any of these issues as far as I can remember, but we have a system in place anyways where whenever we do need to move faster than OpenResty does, we basically will just compile our own Nginx. And so we have a lot of people with that kind of knowledge, so it's not a huge issue for us to just say like, oh, there's a security problem in Nginx. We'll just make the newest version work ourselves. And we'll try to contribute that back so that everybody else can also upgrade at the same time. Yeah.
Xavier, concerning deterministic hashing, you've mentioned. Are you aware of the keys that Google uses for the
keys that Google uses?
You mentioned that you use IP and
so I'm not aware of the full key that Google uses. They definitely use the IP as a portion of it, but they likely, for example, also use what app you're trying to access within Google. And some other concerns like that. The key doesn't really matter too much as long as it's unique enough for you.
That's my point. It's So, and in your case, IP and the IP and the shop ID, I think. Yeah, and is that okay for you? I mean, is it enough? Okay.
Yeah, because every shop ID is going to be unique, and for our purposes, I mean, yes, you could be dealing with, for example, a college campus sharing an IP, but we're not sending that traffic to a single server. We'll send it to, I think we were sending it about to 30 or 40 servers, so that you can still handle large amounts of load through there, and you'll basically send all traffic coming through that key to a random server within that pool of 30.
Okay, that's it for questions for now. Thank you. Another round of applause, please.